So the final thing I want to talk about in chapter 3 is not going to be something that I'm going to test you on or give you homework on, but it's another gold nugget, another kind of nice bit of mathematical information that you might not see anywhere else in the math curriculum here at Wright State, or maybe you do. I don't know. No, that one wasn't. No, that's just sort of a discussion that we were having. All right, the notes are online though for that. Um, um, so we talked about sets and their cardinality, the cardinality or their order. So let's talk a little bit about infinite sets. So, right, an infinite set is one whose order.
You aren't sharing the screen.
Oh, did it stop sharing? Not that. So an infinite set is one whose cardinality is not finite. So one where you can't attach a finite number to the number of elements in the set. So now the question is, do any two infinite sets, or is any one bigger than the other when you have infinite sets? Can you have some sets that are infinite?
Yeah. No bigger infinite.
When you have one set containing another set that are infinite, does one have to be bigger than the other? So, I mean, these are some ideas to explore. Okay, well, let's take a look. For example, so the basic definition. A set, an infinite set, is said to be countable or enumerable when its elements may be labeled 1, 2, 3, 4, 5, 6, 7. So when you can put them in one-to-one correspondence with the positive integers. All right? That is, when the elements of the set can be put into 1-to-1 correspondence with the set of positive integers or natural numbers. The natural numbers, you can put a 0 at the beginning or something like that. Well, however you like to think of it, either one is fine. All right, how about the integers themselves? Is the integers themselves countable? Come on. So is or is not? Can I put the integers? So the integers are the positive integers, the negative integers, and 0. can I put that in one-to-one correspondence with the positive integers? In other words, can I label these numbers 1, 2, 3, 4, 5, so on and so forth?
No.
No? I mean, it doesn't have to be that 1 corresponds to 1 and 2 corresponds to 2. It can be some other sort of correspondence. I mean, let's try. So number 1, number 2, number 3. So I'm going to make an itemized list of the elements of Z. So we'll say 1, let's make it 0. 2, we'll make it correspond to 1. 3, we'll make it correspond to -1. 4, we'll make it correspond to 2, -2. 3, -3. Am I going to get everything? Right, 2k is going to correspond to what in that case? Right, so I got 2 corresponding to 1, 4 corresponding to 2, 6 corresponding to 3. So 2k is going to correspond to
Just K would be 1K.
Yeah, and then 2k plus 1 is going to correspond to
Negative K.
negative k. Did I get it all? Did I get the whole set of integers? Did I list them all in this list?
Yeah.
Yeah. So Z is countable. So in this sense, Z, all right, is the same size as Z plus. Even though Z, the positive integers, is a proper subset of Z. All right, Z plus and Z are the same size. Have the same cardinality. In this sense, they have the same cardinality because I can match the elements together. Since the elements are matched together, cardinalities must be the same. I know one's a subset of the other, proper subset, but that doesn't mean anything. Because things are infinite, you can kind of, stretch stuff out as much as you need to. Right? Okay. How about the rational numbers? Is that countable? No, I didn't hear anything. Check your mic. Maybe you're... Yeah, check your audio settings. Right, the set of all A over B such that A is in Z and B is in Z and B is not equal to 0. Is this one countable? Is or is not, do you think? Is the rational numbers the same size as the integers, as the positive integers? Can I number the rational numbers 1, 2, 3, 4?
Yeah.
Yeah.
No.
Yeah, you can, believe it or not. It's counterintuitive, totally. It's totally counterintuitive, but it is countable. Is countable. I know it's crazy. You think no? I mean that can't be the case, but it is. So here's the enumeration. So 0, right, which is equal to 0 over 1, 0 over 2, etc., etc., etc. that'll be number 1. Okay? That'll be number 1. So anything with 0 in the numerator, that just corresponds to 0. Okay, now, look at z cross z. The Cartesian product z cross z. So x coordinate, y coordinate, where it's integers. Or z plus, positive integer coordinates. Z plus cross z plus. So that's the set of all ordered pairs A, B, such that A and B are both in z plus. So no zeros there. Okay, that's all the rational numbers except for the negative ones. Right? This set accounts for all of the rational numbers, the positive rational numbers, of Q. To get the negative elements of Q, we'll just do the same trick we did with Z. So we will show that, so call it Q plus. Okay, so we'll show that Q plus is countable. And then all of Q will be countable. Using the same trick. That we did with Z. So let's leave 0 out of it as well. Let's leave 0 out of the discussion. So consider this set just Z plus Cartesian product Z plus. And that set will account for all the positive elements of Q. It accounts for more than the positive elements of Q because like 3, 6, right, corresponds to 3 over 6, which is equal to 1/2, which is equal to 2 over 4. It corresponds to a lot of different ones, but that's not going to be a problem. We'll show you that in a minute. So, we're just going to show that the positive rational numbers are countable, or we can put them in one-to-one correspondence with the positive integers 1, 2, 3, 4, 5, 6, so on and so forth, and get all the rational numbers. Okay, and then to incorporate the positive and negative ones in there, then you just redo the counting and you flip-flop positive, negative, positive, negative, positive, negative in the same way that we did before. All right, so let's list it out. 1, 1, 1, 2. Let me make sure I do that right. Yeah, 1, 3. 1, 4. 1, 5. 1, 6. 1, 7. So on and so forth. 2, 1. 2, 2. 2, 3. 2, 4. 2, 5. 2, 6. 2, 7. 3, 1. Leave out the commas. 3, 1. 3, 2. 3, 3. 3, 4. 3, 5. 3, 6. 3, 7. 4, 1. 4, 2. 4, 3. 4, 4. 4, 5. 4, 6. 4, 7. One more row. 5, 1. 5, 2. 5, 3. 5, 4. All right. Well, let's do one more.
Are they supposed to have points in between them?
Yeah, there's supposed to
Oh.
be a comma in between. Yeah, I'll do those in a second.
Oh, okay.
Yeah, I'm just giving my hand a break. Let me do one more row so it's square. 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. Oh, between the pairs? No, I'm just listing them out. So this is all of the Cartesian product, z cross z, right? The way I'm listing it out here. The first, listed according to the first coordinate. Everything with the first coordinate is 1. Everything with the first coordinate is 2. First coordinate 3. So on and so forth. So this is like the first quadrant of the xy plane, just the integer pairs. Just the integer pairs in the first quadrant of the xy plane. Except I flipped it upside down. All right, here we go. Consider the triangles here. 1. So this is the triangle where the coordinates the line where both coordinates add to 2. This is the line where both coordinates add to 3. So we'll call that, that's fine. The sum of the coordinates is 4, right? Sum of the coordinates is 5. Sum of the coordinates is 6, right? Sum of the coordinates is 7. So on and so forth, right? If I keep drawing diagonal lines like that, will I get all of the all of z plus cross z plus? With these diagonal lines, will that fill up the whole square, the whole infinite square, these diagonals?
Yes.
Sure. Okay. But each square, how many things are in it? Infinitely many or finitely many? There's 1 thing here, 2 things here, 3 things here, 4 things here, right? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. What are these numbers here? 1, 3, 6, 10, 15, 21. 1, 3, 6, 10. You ever been bowling before? Right? That's a rack of pins, 4 layers deep. You ever played 8-ball before? That's a rack of 8 balls. It's got 15 balls in it. It's a triangular stack, 5 layers
The
deep.
triangular
numbers, right? Yeah.
The
Like this is the first triangular. Anyway, this number is so I mean, if this is the first, second, third, fourth, fifth, sixth diagonal, this number is 6 times 7 over 2. 5 times 6 over 2. 4 times 5 over 2. And that gets all the pairs. That gets all the pairs. And z plus cross z plus. But then you think, well, with Q, you don't want all the pairs because you don't want to repeat yourself. Right? Well, that's fine. Just anytime you're about to repeat yourself, such as like right here, these are all 1, you just skip it. If we already counted that one, you just skip it and you keep going. The ones you don't skip, those are the ones that are in like row A, column B, where A and B don't have a common factor. Row A, column B, where they don't have a common factor. So like this is row 1, column 2. They don't have a common factor other than 1. Right? But like row 4, column 2 is going to be the same thing. Right? 1/2, 2/4. So that's it. So we've enumerated the entirety of the positive rational numbers. And then the negative rational numbers, you incorporate those just by alternating positive, negative, positive, negative. Crazy, huh? So Q and Z plus are the same size, same cardinality. Even though Z plus is a proper subset of Q. So now the question is, are all infinite sets countable? And the answer is no.
I would imagine the irrational numbers wouldn't be countable.
Oh, that's the rational numbers, what we just did. The real number.
No, irrational.
What's that? Yeah, right. The irrationals by themselves. So R is not countable. R is not countable. Okay, so let's show that. Right, the set of all x such that 0 is less than x is less than 1 is not countable, which is a subset of R. Right, and therefore R cannot be countable. All right, so this is proven, and the only proof that's known is this proof by contradiction. Proof by contradiction. There's no known direct proof. Some people have a problem with this. I don't. So proof by contradiction. Okay, every real number between 0 and 1 so what should we call this? So just call it I. Every real number in I has a unique decimal expansion. Right, a unique infinite decimal expansion. Right, and every infinite decimal expansion not expansion, decimal sequence. And every infinite decimal sequence is a real number. All right, so as long as what? You got to exclude something. All right, like 1/2 is equal to 0.500000000. 1/3 is 0.3333333. 1/6 is 0.16161616. Right? Does anyone remember what 1/7 is? Yeah, well, 1/7 is. It's got a large decimal expansion. Point 142.857. 142.857. And then there's this thing. Right, so these have repeating patterns, but not everything has a repeating pattern. I mean, this has a pattern, but doesn't repeat itself exactly. These are all real numbers in I. So there's a one-to-one correspondence between real numbers and these decimal expansions. As long as you exclude what? There's one non-uniqueness problem. Somebody knows it. Come on.
I mean, you could just add a 0 between the first number after the decimal.
Yeah, those give you a different set of numbers. A different set of numbers. So you take all those things and divide them by 10. So like 1 over 70. Right, 1 over 70 is 0.0142857, 142,857. Right, 1 over 60 is 0.101616. So those are different numbers, right? Right, but how can you get non-uniqueness? How does, one decimal expansion equal another decimal expansion numerically? There's only one way in which it happens. Oh, let's do less than or equal to. But not 0.9999999, otherwise known as
1.
1. That's 1. Did you guys know that? Right, or like 0.1, which is 0.0999999, so on and so forth. Anytime you have that infinite trailing sequence of 9s, basically it all carries over and give you a 1 in the next decimal place. Why is this equal to 1?
I've seen that before and I absolutely hate it.
I love it. It's my favorite math fact in all of math.
Let x equal 0.99999, so on and so forth. So 10x equals what? 9.99999. So 10x minus x is equal to, well, it's 9x, but that's equal over here on the right.
9.
9.
Also, we already just confirmed that 1/3 is just repeating 3s. If you just times 1/3 by 3, you get 0.9999.
Yeah, that's a nice point. Yeah, I never thought about that. Yeah, if you take 1 and multiply it by 3 over here, you get 0.9999999. So that's supposed to be 1.
For the
That's
for
nice. What's that?
So apparently, I saw a video that was proving that infinite 9 is 1 in 10 different ways.
Yeah, there's different ways to do it. That's one of the most straightforward ones. They're all sort of straightforward. There's another proof using well, you guys all took Calc 2 already, using infinite series. So like the geometric series, the sum n equals 1 to infinity. Sum n equals 1 to infinity. Oh boy, we're way over time. I'm sorry, guys. All right, we'll finish that next time. All right. So please get started on assignment 3 and come to me Monday with questions, okay? And we'll finish up this, show you how the real numbers is not countable, okay? All right. Okay, guys, have a good weekend, and we'll see you then Monday.